This lesson's on solubility and ionic equation. We will look at solubility rules, molecular equations, complete ionic equations, and net ionic equations. The first thing you understand is that ionic compounds will dissociate in solution, and a dissociation is the separation of a soluble ionic compound into its ions in solution. For example, if we take solid sodium chloride, aluminum chloride, this is a soluble ionic compound, put it in water, it will dissociate into the ions that compose it, an aluminum ion and 3 chloride ions. Visually, it might look something like this. Here's the solid, all bonded together. In water, the ions all dissociate or separate from each other. The more technical term for this is solvation, in which the water molecules will surround each ion and hold them in solution. There are rules to determine if a ionic compound is soluble or insoluble. They start out with things that are soluble, so all nitrates, acetates, and chlorates are soluble. That is, they will dissociate when you put them in water. All salts of alkali metals, group 1A, so lithium, sodium, potassium, rubidium, cesium, and so on, are all soluble, and ammonium salts are always soluble. So if I give you this list, all of these are soluble. Sodium chloride contains sodium, ammonium phosphate because it contains ammonium, and Rule 2 says ammonium salts are soluble. This one is soluble because Rule 2 says ammonium compounds are soluble, and Rule 1 says nitrates are soluble. This one is soluble because of Rule 2 saying lithium ion salts are soluble, and acetate salts are soluble. This one is soluble because Rule 1 says chlorates are soluble, and this one is soluble because all potassium salts are soluble. So again, we're starting with things that are soluble. When you get to the third rule, now it says most chlorides, bromides, iodides, salts of the halogens are soluble, except if it's a lead 2 chloride, bromide, or iodide, and same for the silver or mercury. So magnesium bromide is soluble because it's not a lead, silver, or mercury halide salt. Calcium chloride is soluble. Silver chloride, though, is insoluble because it is a chloride with silver, and silver is one of those insoluble halide salts. Mercury 2 iodide is insoluble because it contains the mercury 2 ion. Strontium bromide is soluble, and lead 2 chloride is going to be insoluble because lead, iodides, bromides, chlorides are insoluble. Sulfates are soluble except for strontium sulfate, barium sulfate, and lead 2 sulfate. And so if we look at this list, magnesium sulfate is soluble. Barium sulfate is insoluble because it's one of the exceptions to the solubility of sulfates. Lithium sulfate is soluble because it's not one of the exceptions, and it does contain a lithium salt, or lithium ion, and lithium salts are soluble according to Rule 2. When you get to Rule 5, now it's describing things that are insoluble, that is, will form a precipitate or not dissociate in solution. And so all of these are going to be insoluble except for lithium hydroxide, because that is a group 1A hydroxide. And ammonium hydroxide is going to be soluble because, again, Rule 2 says ammonium salts are soluble, and that will include the hydroxides. Calcium hydroxide is sometimes considered slightly soluble, so it's kind of borderline in between, but we will consider it insoluble. Rule 6, most sulfides, carbonates, chromates, and phosphates are insoluble. The only soluble ones are going to be those that will agree with Rule 2, that is group 1A, phosphates, carbonates, chromates, sulfides will be soluble, and ammonium salts of those will be soluble. So calcium sulfide, insoluble. Potassium sulfide, soluble because it's potassium. Aluminum sulfide, insoluble. Lithium sulfide, soluble because it's got lithium in it. Ammonium sulfide, soluble because it's got ammonium in it. Iron 3 phosphate insoluble, whereas these last two are soluble because again of rule 2, group 1A salts, ammonium salts are soluble. Same for the carbonates. Aluminum carbonate is going to be insoluble, sodium carbonate soluble, potassium carbonate soluble because those are group 1 metallic ions. So if a compound is soluble and we put it in water, it will dissociate. So if we look at magnesium chloride as a salt, the solubility rule says chlorides are soluble except for lead, mercury, silver. This is not one of those, so it is soluble. So when you put it in water, it will dissociate into its ions. It's made up of a magnesium ion, 2 chloride ions, so we get a magnesium ion and 2 chloride ions. Barium hydroxide is one of the soluble hydroxides considered to be a strong base, and so it will dissociate into a barium and 2 hydroxides. Aluminum hydroxide, however, is insoluble and will not dissociate, so you do not get a precipitate. It will not dissociate in solution. A little bit of a disclaimer here. It does dissociate to a very small extent in what we call equilibrium with the double arrow, but that is something we're going to cover later in the course. So for right now, you can consider it to not dissociate. Iron 3 nitrate, according to rule 1, nitrates are soluble. And so iron 3 nitrate is going to dissociate into an iron 3 ion and 3 nitrate ions in solution. And again, we know it's iron 3 nitrate because the nitrates of 1 minus, 3 nitrates give you 3 positives. Barium sulfate is insoluble, so it will not dissociate in solution. So you need to use the solubility rules to determine if a salt is going to be soluble or insoluble. If it's soluble, it does dissociate into its ions. If it's insoluble, it does not dissociate into its ions. And again, technically, that's not absolutely true, but for our purposes right now, if the solubility rules say they're insoluble, we will treat them as not forming a precipitate at all. So at this point now we need to get to ionic equations which show how ionic substances react to form new substances. It shows aqueous ions as ions, not as an ionic compound, because again, as soon as you put, say, aluminum chloride in water, it no longer acts as aluminum chloride because it dissociates into aluminum ions and chloride ions. These now can act independently of each other, and so you have a mixture then of aluminum ions and chloride ions and not a compound. And then we'll also look at net ionic equations. They show only the reacting ions. They don't show the spectator ions. So first example here, aluminum chloride and silver nitrate. The idea here is if I take an aqueous solution of aluminum chloride, which again is just a mixture of aluminum ions and chloride ions, and I combine it with an aqueous solution of silver nitrate, which really is just a mixture of silver ions and chloride ions, by combining these together, I could possibly get a precipitate, and the possible precipitate will be the silver and the chloride, or the aluminum and the nitrate. So if we look at the solubility rules, aluminum nitrate is going to be soluble because nitrates are soluble, but silver chloride is going to be insoluble because chlorides are not soluble with silver. And so now if we get a precipitate, the silver chloride, we then need to write the molecular or chemical equation. So we start with the compounds we're given, aluminum chloride. And so aluminum chloride is AlCl3, and silver nitrate is AgNO3. And then this is going to be a double replacement reaction. We're going to switch the silver and the aluminum ions, and so we will end up with not aluminum chloride and silver nitrate, but silver chloride and aluminum nitrate. And so the product is going to look like this. The silver chloride is the precipitate, and S here does not stand for soluble, stands for solid. And aqueous aluminum nitrate, that is soluble, so it's going to be aqueous, dissolved in solution. So we do get a precipitate, a solid that forms. Now again, everything that is soluble is going to dissociate. So aluminum chloride is aqueous. It's going to dissociate into its ions. So when I write the complete ionic equation, I want to show aluminum chloride as dissociated. So aluminum chloride dissociates into 1 aluminum and 3 chlorides. Silver nitrate dissociates into 1 silver and 1 nitrate. Silver chloride on the product side does not dissociate. Remember, it's insoluble. Insoluble compounds do not dissociate into solution, so it stays as the solid. And aluminum nitrate is soluble, so it will dissociate into an aluminum ion and 3 nitrate ions. Note, this is not a balanced chemical equation. We're not going to balance them at this point. We will do that later on. I'm just rewriting this entire equation to represent it as it truly is in solution with all the soluble ionic compounds dissociated. If we note on the complete ionic equation, the nitrate ions are uncombined on this side, uncombined on this side. The aluminum ions are uncombined on this side, uncombined on this side. In other words, they are the spectator ions. The only ones that really change are the ones that form the precipitate. And so if we want to write the net ionic reaction, what I always suggest is you write the precipitate first and then work backwards, asking yourself what ions are going to form the precipitate, and the answer is 1 silver ion, 1 chloride ion form the precipitate. So the net ionic reaction shows only those ions that form the precipitate. All the rest of the ions we call spectator ions. They stay in solution. Visually, it's going to look like this. If I have aluminum chloride, I really have a bunch of aluminum ions and chloride ions floating around in solution. The silver nitrate, I have a bunch of silver ions and nitrate ions floating in solution. But if I combine these two together, then the positive ion of this one may combine with the negative ion of this one, and the positive ion of this one may combine with the negative ion of this one. And in this case, the silver ions and the chloride ions form a precipitate which settles out of solution, and the aluminum and the nitrate ions stay floating around. So again, these are the spectator ions. They just stay floating around, and the silver chloride are the ions that form the precipitate, and so they show up in the net ionic reaction. One more example. If I take magnesium nitrate and copper 2 sulfate solutions, again, both of these are soluble and aqueous, and I mix them together, then a possible precipitate could be copper 2 nitrate or magnesium sulfate. Copper 2 nitrate is not going to give me a precipitate because nitrates are soluble and sulfates are generally soluble, and they are soluble with magnesium, so that's not going to give me a precipitate. And so if there's no precipitate, you do not need to write any of those reactions because all you're doing is mixing ions together. Visually, it's going to look like this. Here we have aqueous magnesium nitrate, so magnesium ions and nitrate ions floating around in solution. Here we have copper 2 sulfate, copper and sulfate ions floating around in solution. If I mix them together, there's no new precipitate. The positive ion and the negative ion of this one will not form a precipitate. The positive ion of this one and the negative ion of that one will not form a precipitate. So all we do is form a mixture, a physical combination of all those ions. Since there's no precipitate, no chemical reaction, no reaction to write, and so you just have to write no precipitate.